Good evening once again. More 10.2 parametric equations and calculus. So I just went over with you guys in my last video. Just really quick, we went over how to get the derivative with parametric equations and the second derivative, which is just the derivative of the first derivative. We didn't do any examples with them, but I gave you where those formulas come from. I posted other videos that show those examples of using them. Now, what I want to do is go over arc length. And I'm going to use the explanation I made before for arc length. And that is where, okay, we use these small little lines and then get the little lengths of each of these lines and put them together. Have an infinite number of lines, infinitely small, and we'll get the actual length of the arc, or the length of the curve. And what we do is we take any section here, the ith section here, get a rectangle. Here, get the hand so you can see this better. The rectangle, or the triangle, I should say, and one side is delta x, the other side is delta yi, because right, the change in y is different for any change in x. And we got that this was the length of any little section was the square root of delta x squared plus delta yi squared. And I could have put delta x sub I squared if I wanted to. And because, well, they were all the same, so it didn't matter, but I could have. And so let's just move on with this. I'm going to copy this. And let me see if I can copy two things. And then one more trick, too, that we did in order to replace the delta y sub I squared, we used the mean value theorem to rewrite, well, this was delta yi as f prime of x star I times delta x. Well, here's a question for you. Would it be okay to do something similar with delta x, especially to say if, because, well, what is delta y? Well, delta y is always, y is a function of x, right? So we could do this. Well, what if y is a function of t and x is a function of t? Well, then I could do it for both of them. And so the quick explanation, and there is this one in our book also, is, well, do it for both of them, right? This is going to turn into an expression much like this. And I'll do that substitution for both. So I want to do that really quick with you. I'm going to paste this in. And we're going to do exactly that. Is that change in t is what's being constant. And so in each of those, let me see here. Forgot to put my gloves on. Okay. Anywho, so because of the mean value theorem, again, we could go ahead and we could make that same statement we did before. Since both of these are functions of t, very, very similarly, we could say that, in our case, we're going to say x is f of t, y is g of t, and therefore, delta x sub I could be the same as f prime of t sub I star times delta t, and delta y I could be the same as g prime of t sub I star delta t. More or less. more or less. It's the same thing. We could do a very, very similar thing. And so what do we get? We get that any of those little chunks could be written as the square root of f prime of t sub I delta t squared plus f or g. Oh, am I hitting the wrong button again? No, I guess not. I don't know what's going on. There we go. Plus g prime of t sub I delta t squared, and then we can easily factor out the delta t squared in order to get that each of these little approximating lengths can be approximated with f prime of t sub I squared plus g prime of t sub I. Oh, and I should put the square a little bit more clearly. I'm squaring this. And then we're going to square this guy. And then that delta t squared can come out as delta t, which is perfect since we want an integral in terms of t. We're doing an arc length with parametric function. So f is in terms of t, x is in terms of t, and y is a function in terms of t. So our arc length, let's say L, is about the sum of these L sub i's. And if I take, from I equals 1 to n, however many I have, and if I let the limit as n approaches infinity, then what I get is the actual arc length will be the integral from t equals alpha to beta of the square root of f prime of t squared plus g prime of t squared dt. And that is where that formula comes from. And again, the Leibniz notation sometimes a little bit more friendly when it comes to this stuff. So let's write it in Leibniz notation. Again, it would be alpha to beta. F prime of t is the same as dx dt. So square root dx dt squared plus g prime of t, that's going to be dy dt. Squared dt. Both of these are perfectly acceptable for arc length. And in fact, our book will just say ds. We'll just say, you know what, this whole thing here is, we're just going to say that's ds. And we use that a lot in formulas in our book. ds to be the arc length. Any questions? Tough. This isn't live. If you're watching this right now, actually I am looking at the chat, but in any case, I don't think anyone's watching because I think you need the link. Anyway, I'm not going to do an example. I just wanted to show you that. But this does lead us to doing, let's say, an area of the surface of revolution. Is that, hey, why not? We could still do an area of a surface of revolution. And so, why not show the surface area of a sphere of radius r? That's always a fun problem to do. So let's do it. So we have arc length. it is this. It is either of these, and that is assuming, again, don't forget that x was f of t and our y values were g of t. Okay. Now, let's do an example. So like I said, show the surface area of a sphere of radius r is 4 pi r squared. So show that the surface area of a sphere, I'll write it out, show the surface area of a sphere of radius r is sorry 4 pi r squared. All right. Could we do this without Cartesian without parametric equations? Sure we could. But let's try to do it with it. So what we'll do is rotate a sphere, and we know how to do rotate a semicircle about the axis. So let's imagine we got this semicircle right here, this beautiful semicircle going from negative r to r here, and we're going to rotate that around. Oh, actually, I take it back here. Let me see. Let's double check this here. Cosine of pi. Okay. No, that's right. So there we go. Okay. So, and we're going to let, so we'll pretend this. So what is what are the parametric equations for this? Well, it's x equals r cosine t, and y is the same as r sine of t. There we go. Parametric equations. Let's double check this. So t, and oh, by the way, well, for what values of t, right? We need that. So let's say t is going from 0 to pi. So let's see. My x values should go from negative r to r. If we, and x is the cosine. So if we plug in 0, cosine of 0 is 1, times r is r, bam, we're here. Let's say we're cosine pi over 2, well, that's 0. R times 0 is 0, so you're probably, scooting back this way. And then cosine of 0 is, I'm sorry, pi over 2. Okay, now cosine of pi, well, that's negative 1, and negative 1 times r is negative r. Okay, so we're moving this way. Let's see if the y values are doing that too, going from 0 to 1 to 0. If we plug in 0, r times sine 0 is 0. If we plug in pi over 2, sine of pi over 2, well, we can do a quick little sketch here. Sine, that's pi. So pi over 2 is right here. Pi over 2, that's going to be 1. Yep. So that'll be r here, right? That's r. And if I plug in pi, sine of pi is 0 again. So yeah, there it is. So there's our semicircle going from 0 to t. And so we can imagine that, let's say at some value for t, let's say here, there's my t sub I, that we are going to take kind of this little section here, let's say this little section here, and rotate that around the y or the x-axis there. just like we normally would. Well, what is our formula for surface area then? Well, it's usually what? Something like this. It's going to be the integral from a to b of, well, what are we doing? We're doing 2 pi r. We're kind of taking the segment and we're bringing it around this circumference. So it's 2 pi r, or radius, or I might say r of x usually. Whatever we're using for radius, that's usually what we do, times arc length, times ds, I said, or just whatever arc length is. Okay, so for us, we're going to do the same thing. We just went over a formula for arc length, and our r in this case is the y value, which we got right here, our y value. So our surface area is going to be the integral from 0 to pi of 2 pi, and in this case it's y is that length, ds. And then I'm going to go ahead and one more step, plug in. Well, what is y? Y is, I could bring that 2 pi out front also. Why not? Don't need it there. Y is r sine t. So plug that in, r sine of t. And then arc length, or that formula for arc length, that ds here, that little length here, this little segment that I'm rotating around, that guy is, oh yeah, it's just the square root of dx dt squared plus dy dt squared. Okay, so I got one more step. Well, what is dx dt? What is dy dt? Let's do it over here, and let's just bring this out here. Well, there's x, so what is dx dt? So take the derivative with respect to t. dx dt, oh, and then don't forget dt here, is r, derivative of cosine is negative sine. So negative r sine of t, and dy dt, the derivative of y with respect to t is r cosine t. All right, now we just plug it all in, and we will be done, and we know what the answer should be. It should be 4 pi r squared, so hopefully we're not messing up. No whammies. 2 pi times 0 to pi. Yep, my value's for t. Okay, and let's see here. R sine of t times, and hopefully this just turns into a 1. I feel like, oh no, an r, right? Looks like it's being r. dx dt is r sine t. Square that. What is that? That's r squared times sine squared t. And then I got plus dy dt, which is r squared cosine squared t. Oh, it's a beautiful thing, because that is just r squared times the quantity sine squared plus cosine squared t, which in other words, all that in the root is nothing. It's nothing. It's coming out 0 to pi. Those are my limits on my integral. R times sine of t. And what is this? This is going to be turned in r squared times 1. What's the square root of r squared? R dt. I think I'm almost ready to do this. And some of you might be thinking, because you're so fast and you're keeping up with me, thinking, hey, wait a second. There's r's and t's in here. What's up with that? Well, remember, r is just a constant. Like you would choose what r is first, right? The surface area depends on r. So we're just going to treat that as a number. In fact, I could just, that r times r, I could factor that out. Just take it out here, it's r squared. So I just have, I can write that a little better. Give myself some credit here. Okay, r squared. That's just going to be sine t. Oh my goodness, I think I know the integral of sine. I hope I do. If I don't, I have no business teaching Calc 2. 2 pi r squared times integral of sine is negative cosine of t dt. No dt. 0 to pi. Now, you know the answer should be positive. If you do all this work and you get a negative, you got like, oh, there's no surface area. No, that's like saying I have a negative distance. That's bad. We're not having a negative distance. We're not having a negative surface area. So I already know. No, I'm not going to be wanting that. Let's make sure this is working. 2 pi r squared. Okay, plug in pi. Cosine of pi. What is that again? Negative 1. So first I have negative of negative 1. 1 minus, plug in a 0. What's cosine of 0? And if you don't know, I'm just looking at this. Cosine of 0 is 1. So minus negative cosine of 0 minus negative 1. That's 2. So 2 times 2 pi r squared is 4 pi r squared. Is that what I was looking for? Yes. It is exactly what I was looking for. We did it. We're amazing. We got surface area. So there's an example of using surface area, and here's my illustration that the formula for surface area hasn't changed at all. The only part that's really different is that radius a lot of times will just be one of your functions, right? In this case, y is a function of t. We're just going to plug that in. And our arc length part, which is what surface area of a, or when you get the area of a surface of revolution, was something very similar to this, but now it's changed. You're still just plugging that in. So it's not really any different. You just have to remember the surface area or the arc length for a surface, the arc length for parametric equations. That's all you have to remember, and everything else is pretty much the same. So there you go. Our book does try to simplify it down to saying, you know, it's kind of like this. You're going from t is alpha to beta of 2 pi y ds. ds is that arc length part. It's this root part. And, you know, that's if you're rotating about the x-axis. If you're rotating about the y-axis, well, then your radius would change, right? And you'd be going from alpha to beta of 2 pi x ds. ds, that arc length part. Okay? And a lot of times it is that simple, but you know me, I like to have at least some kind of a basic sketch like I have right here, just to make sure I really, like y in this case was my radius that I am envisioning here. What if it was moving up 1, I was rotating around like, what if I was rotating around x is -1, right? Then okay, it's going to be actually y plus 1, right? And again, you'd replace y with whatever expression I have for y, but you know, be careful about that stuff. Okay. There's surface area. So what did I want to do? I wanted to do, what is the title of this? I think it's arc length. Got it. We covered how to get arc length. It's this. Surface area. I even did an example. of surface area, which is a lot like doing an example of arc length. Great, did that, it's awesome. And now I want to do an expression with area. So, let me see, how long have we been? Oh my goodness, 25 minutes. This one's a little bit longer. Well, let's talk about area. You know, hey, we're getting the area under a curve from A to B of y equals f of x. This is what we normally do. Right? And if we want the area under the curve here, all of this, what we'd normally just say is area is the integral from A to B of f of x dx. But now that's not what we have, is it? Now what we have is, well, y is a function of t. So y is, and we've been using x and y. And I've been using lowercase f for my x value. So actually, I'm going to make this a capital F. So let me make this capital F. So I'm consistent here. So normally we say, yeah, y is f of x, and the integral will be the integral of f of x. But now what we're doing is we're saying, hey, no, actually, x is a function of t, and y is a different function of t. So we're going to say x is f of t, y is g of t. So how do I take the integral now? Well, this is how. Let's do a substitution. We can use a substitution rule like a u sub in order to get the area, and you can memorize it, but this will work. Well, what is f of x again? It's y. It's y. So actually, okay, a is the integral, and it's of y. And of course, y is g of t, but one thing at a time. So y dx. So wait a second. And it's from a to b, I guess. And that, remember, a to b, that was x equals a to b. Does t equal the same thing as a here? No. T is going to be some totally other value. Who knows? Right? We've got to figure that out. But we can totally figure it out. You know, whatever t value is when x equals a. Let's say when x equals a, t equals alpha. And let's say when x equals b, t is beta. Let's just say that for now, just for our own sanity at the moment. And let's do that, because what happens when we do a substitution? You use substitution a lot of times. Well, we're switching from x values to t. Well, we have new limits of integration, right? Okay. Well, we're going from alpha to beta now. What else? Well, y is actually g of t. Okay, so I'm going g of t. And dx, well, what's dx? Dx, well, what's dx is right here. Take your x equals f of t at the top here, and take the implicit derivative of both sides. What do you get? You get dx is the same as f prime of t dt. Well, there we go. So what is my area under the curve? It is alpha to beta of g of t. Dx was f prime of t dt. Oh, it's amazing. And this is the formula our book uses. I'm fairly certain. Let me see. I'm going to double check right now, because it should be. Oh, there it is. Let me see here. Yes, that is what the book has. Yay me. Yay you guys. So that would be it. that is the formula for area under a curve. And now if you had an area under a curve, but you were, say you had a curve like this, and you're going from C to D, you know, right in here, and we wanted that area, we want this area. And maybe we'd say X is a function of Y. I think you could do the exact same method and come up with something that would work here. At a glance, I'm not going to say it is, but my guess would be it would be f of t times g prime of t. And then, of course, figure out what t is here and what t is here. Or switch them around. Maybe I want t down here and alpha here and beta here. But in any case, there you go. Okay. So really neat. There it is. And working out an integral like this is very similar to the one we just did. I'll tell you what. I'll start an example. Just to get you kind of knowing how to get started on these, because that's probably the hardest part. And then in class or class meetings, if we need to go over these more, we can do it more. So let's say I wanted to find the area under one arch of the cycloid. Find the area under an arch of the cycloid. Again, guys, remember this thing is the important thing. That's how we get area under a curve if we're dealing with parametric equations, okay? And you saw me figure it out. Actually, it wouldn't be that hard to memorize how to figure it out, so you don't have to memorize this formula. But I'll leave that up to you. Okay? Because there can be a lot of memorizing in this chapter, or there can be a ton of memorizing in this chapter. So find the area under one arch of the cycloid. Well, let's see. The cycloid was x equals r times theta minus sine theta. And y is r times 1 minus cosine theta. So, well, the first thing you'd have to do is do the work and figure out what is one arch of this guy. Like, what values for theta get me one arch? If you don't remember, it looks something like this. I did it in the video today. Earlier video, I showed you this little graph here. So, you know, what's a t-value here? What's a t-value here? Well, I know what the x value is there. Really easily, it's 0. So if you're going to figure out what values for t, or in this case theta, are going to be our limits here, plug 0 in for x and solve. All right? And maybe that's something, if you guys don't know how to do that, maybe we can explore that in class a little bit. But I'll plug in 0 here, and what values for theta will I get? Well, I get 0 and 2 pi. I guess we know what x is here, because we remember it's a circle with radius r. So the circle one full revolution is right there. So that this distance would be, at least for x value, this would be 2 pi times the radius. But anyway, 0 to 2 pi, that would be our t values. So I suppose you could plug in 0 and then plug in 2 pi r. Oh, I'm sorry, it's x values. The x values wouldn't be 0. The y values are 0. The x values are 0 and 2 pi r. But you get the idea. The y value is 0 here, and 0 here, and 0 here, and 0 here. The x value there is 0. The x value here is 2 pi r. The x value here would be add another 2 pi r, so 4 pi r, and so on. So you can plug all those values in and solve for r. It's just a little algebra and trig. Okay. Anyway, let's solve this thing. So find the area under one arch. Well, I already got the area. I know the area. The area is going to be g of t times f prime of t. So g of t, f prime of t. I'm just going to take it nice and slow. dt. Of course, I guess I should put in thetas. We're doing theta, so let's just put in thetas. Why not? G of theta, f prime, theta. All right, well, what's g of theta? Well, remember when we wrote this formula up here, that was our function for y. So, well, what is y? Y is right here, r. And I should change colors, make this a little easier for you guys to look at. R is, I'm sorry, our function for g of theta is the y, so y is r times 1 minus cosine theta times f prime of theta. Well, that's taking my x and getting the derivative with respect to theta. Well, what is that? I'll do the work over here. Dx dt, or I'm sorry, I should say dx d theta is going to be r, because I would distribute this r in, minus, let's see, derivative of sine is cosine, so minus r cosine theta. Okay, so now I can totally plug that in. So I can plug in that. That's going to be r minus r cosine theta. And then dt, oh, let me see here, dt. Oh, it would be d theta. I'm sorry, it'd be d theta here. Where's my d theta? Well, actually, let me double check here. I did f prime of t dt. Where did that come from? dx. Oh, yeah. So, d theta. D theta. Oh, yeah. Well, it's just d theta. It's going to be d theta. What am I talking about? There. D theta. My bad. What am I doing? I'm using a formula here. D theta is part of the formula. Okay. There it is. Now, hard part's done. Now what you would do is you would integrate from 0 to 2 pi of this beautiful thing. You'd first want to factor out the r, and maybe factor out r from here, and this r, so you'd have an r squared out front, and distribute all this, and then integrate it out. And eventually what you would get, what you should get, is r squared times 3 over 2 times 2 pi, or 3 pi r squared. So I encourage you to try that out, see how you do. and let me know if you guys need any other help. Okay? That is all. You guys have a fun time.